Hello, everyone. This is the series of directly from developers' newest features in Mathematica version 12. My name is Dariia, and here tonight with us is also my teammate and colleague Konstantin. And we'll be showing you the work that we've done in the field of cryptography. So this is the page of the newest features in Mathematica 12, and there has been significant development since the version 11 in the various fields, and there have been talks from the developers before, which you can see on the playlist, and there are probably going to be more talks after mine, but tonight we are talking about cryptography. Cryptography, I have to say, is a subject that I am personally very passionate about because it is a very unique intersection between elegant math and very practical usages. Cryptography in Wolfram language as a separate thing, as a Packlet, has existed, if I'm not mistaken, since version 10. But this is the first time it appears publicly, so to say, as a promoted feature. And it has become a loud word in the modern era of cryptocurrencies and blockchains. And since version 10, between version 10 and 12, there has been a lot of things added: encryption, keys, symmetric keys, symmetric, which means that is a one shared secret key between two parties, and asymmetric, that says that the parties that want to communicate share a public and private key pair. Various things for hashing, for encrypting also files, for putting digital signatures on your things. And what we can start with is going through the bullet points here. So Wolfram language has had a lot of different hash methods, and into the version 12, we can click here updated and see that there has been many new hash methods added. For example, if I'm not mistaken, this one is used in Bitcoin or in Ethereum. So there are a lot of methods you can hash your data now. And the significant thing that I'm actually proud of doing for cryptography in version 12 is digital signatures. For example, what you can do now is you can generate some keys. And it's going to be an elliptic curve keys. And this is also a new thing in 12. We are supporting an elliptic curve. The CECP 256K1 is probably one of the most popular curves in the field that is well, it is popular before because it has a pretty small size, but still provides substantial security. And it has been adopted by most of the cryptocurrencies, which makes it the first choice for the curve that we wanted to support, and makes her the foundation on which we can start supporting more curves, which we eventually plan to do. So what you start with is you generate a key pair, which consists of your private key and your public key. Private key you keep for yourself, of course, as you can say from the name. And then public key you want to share with people. You can publish it on your website, for example. You can send it to someone. You can save it in a file and also send it to someone. You can publish it on Wolfram Cloud. And I'm also going to show in these examples how to do various of those things. So let's create a message, which is probably, let's say, which test. Oops. Okay, fine. What we want to do, if we want to create a digital signature to this message, which is going to say that it signs the exact this content of this message, and that the only person who is able to sign it is me, or whoever is the holder of this key. Digital signature of message using the private key of our key pair. Boom. And we get this nice digital signature object that we can see what it has inside. Well, basically says that that's an elliptic curve type digital signature based on this curve. Using hashing method is SHA-256, which is also one of the probably most commonly seen hashing methods, which says that we first hash the content of the message using this method. And we use a non-deterministic way of deriving a signature. And the two important things here are R and S, which are the two parts of elliptic curve signature. And elliptic curve signature is not just a number, it's two things. There are other types of digital signatures. In version 12, we only support as the first one, the elliptic curve one, but already in development, we do have supported the signature also based on RSA, but it's not public yet, which is going to be public in the next version, 12.1, that I believe is coming out pretty soon based on how people are wrapping up their work. And so I've created the signature with the private key that is mine. And now anyone who has my public key can take it and can verify it that for this message, this signature with my public key has to be valid. And in fact, it is. And for example, if somebody writes a different message, it's false. Or if somebody takes a different key. So the signatures are useful for establishing who is the owner of the content and the integrity of the things we're trying to sign. So this is, from my side, the most significant things that I did for version 12. There have also been other important things like encrypting files, which is pretty useful if you're dealing with some confidential information or you want to hide the results of your research, for example. Digital signatures have also been useful for creating transactions to cryptocurrencies and blockchains. And there has been already a talk on blockchains recently, like if I'm not mistaken, 1 month ago. And Christian Pascal was talking more about how this stuff that we have in cryptography also is related to cryptocurrencies. This is related to cryptocurrencies as well. And I guess we can go through some interesting examples that we have invented to show the usability of the things that we have done. This example is talking about how you can publicize your key, so to say, to allow people from anywhere to basically send you encrypted messages without even having to go through encryption, decryption to get in your key, trying to search your key, whatever. Okay, so what we first do, we generate RSA keys. And what you can see is the difference between RSA keys and elliptic curve keys is the size. That's why many applications have preferred elliptic curves, because they only take 512 bits to provide the same level of security as RSA keys that do 2048 bits, which is in the amounts of memory that modern computers have, absolutely insignificant, but still a very nice if you're dealing with huge amounts of keys and the huge amounts of data, and also transferring them through channels. So what we do here is we created keys. Next, we have used nice capabilities that I really like in our Wolfram Cloud in form functions. Because I am not a person who can just go and write a website, but evaluating using form function and cloud deploy, I just evaluate this simple thing that is going to have a place that one can submit a message and just receive it. It's going to be a nice looking website. And I do really like it. That's good. So here you can see that it's a form where one can enter a message. And how do I get where this is actually located? I have to deploy it first, because right now it's just a form. And I deploy it, and this is my lone user ID. Now I'm just going to get this very nice form here. I can enter a message to myself. Let's try this message. Maybe in the talks like this, one should try more difficult messages. Because if you're trying to encrypt things and they are always test message, it's pretty easy to guess. And we can see here that it has placed my encrypted message in a different object. What I can easily do now, I can just get this thing. Oops, it's a documentation page. I am sorry. Yes, this gives me a little tiny, nice encrypted object that nobody is going to be able to decrypt except me. For example, what we could do is we decrypt it with keys. And yes, we've got a test message. If you can see in this session, I have evaluated keys variable being RSA here, but before I have evaluated key variable being elliptic curve here. So for example, if I have forgotten or mistaken and tried this is not going to work because it's a different private key. And I hope, yes, it says it doesn't like it because Decrypt doesn't support elliptic curves, because such thing as encryption and decryption on elliptic curves is not a well-established cryptographical concept, so to say. So one, while managing their keys, managing his keys, should be attentive which key they're trying to use to do things. Because if I'm going to have my keys that are elliptic curve keys, and at the same time I'm going to have keys that are RSA keys, I have to not forget to distinguish between them. So this is a nice little example of how one can set up a personal income box that is going to receive encrypted messages, which I think is pretty cool, given that it's taken such a small amount of code to do. Well, another pretty related thing to this is how making people know your public key is, for example, sharing it as a QR code. And this example utilizes, again, keys based on elliptic curves, because we decided to do it also connected to blockchains, and it's pretty handy for cryptocurrency geeks and fans, because, once again, how many lines of code are here? 1, 2, 3 lines of code. You can just share with anyone your Bitcoin handle, and somebody can pay you with Bitcoin. And in version 12, we also support Ethereum, and I guess soon we're going to be supporting ARC. And the thing you do after generating QR code of your key, you put it on your cloud, and so you can send, you can open this link on your phone, and you can show anyone from your phone this QR code, and they're going to be able to obtain your key or your blockchain wallet. I mean, if anyone wants, feel free to send some Bitcoins to our documentation wallet. So if we have already been talking about digital signatures, let's see what this example has shown you. Oh, well, it has been almost the things that I just showed you, but it also shows you that if you want to save your key, let's regenerate these keys so we're not mistaken. So when you generate your keys, if you run some code for publishing your public key, but then you forget to save your private key, you're never going to be able to access the things that have been signed with this private key or encrypted. For example, if somebody has your public key and they try to encrypt something and send it to you, but you have lost your private key, you have not been able to access it. So it's important to save your private key, and we're doing so by exporting it as a Wolfram language object. I am also working now on being able to export it as a more standard of things and file extensions like .pm and .key, which are common to all the operating systems. So this is also coming, better key management. And so what we did here is we have saved our private key, so we did not lose it, and we were able to use it again. And we want to publish our public key. And because we want everyone to use it, so we did. And now, well, this is a pretty long user handle. I think there is a way to get it with your name in it, but I do not remember that on top of my head. So for now on, let's just use this long handle. So if we want to sign a message or use this private key, it's pretty easy. What we do, we just import it back, and you see we got that same nice rendered object that has, well, this is a totally unsafe thing to do, and please do not do this at home. But I'm just going to show you this private key that is generated, which is supposed to be private, but I just want to show you what it has inside. It has a curve handle. It has a public curve point, because a public key and elliptic curve is actually a point in an abstract mathematical representation of a curve, which actually is nothing like a curve on the it's just a scattered thousands and thousands of points on the plane, but it is called a curve. So this is basically x and y coordinates of this curve, which is your public key, and your private key is an integer that is a multiplier. So each curve has a generator point, which is like a basis point, a foundation point for calculations of public keys and all other operations on points on this curve. So your public key is basically your private multiplier multiplied by this generator point. And this also says that it's not compressed, because there is a way to generating it compressed, which is basically just storing the x coordinate here without the y coordinate. Just takes even less space. Instead of 500 bits, it takes 200 bits. And byte arrays of these keys for faster calculations. Let's try to sign a message. And now we can put this, also the message itself, on cloud, so anyone who wants can access it. Well, not the message, but also the signature. So anyone can access it, and anyone from all over the world can go and verify that this particular content here was signed by the person who has this private key and who has this public key that has been published. We can get the message, And the beauty of this, that it can be done from anywhere or with any other Wolfram user, because right now it doesn't make much sense if I'm doing it for myself, just getting messages and signing them and checking them. I remember it was pretty fun when we were working on this, and I was sending other people in the company this links to my keys and signatures and asking them to check for me my uh, check if my encrypted emails are actually decryptable, and that the things that I've signed are actually unsigned, are verifiable. So, and in the beginning of work, of course, it was not always verifiable or always decryptable, but it was pretty fun. And yes, we're verifying that the signature was signed by a person who has the private part of this public key. Well, also now, if you were very careful and did all the screenshots of the private key that I was showing here, you should be able to decrypt and get back this message and start signing things in my name. But I deny ownership of this key. This is just for this video session. So these are pretty practical things. We have a similar example here with this nice little bird for establishing the authorship of an image, because here we were doing, in the previous example, just a message that is a text, which is kind of boring. But because, for example, a picture is also easily convertible to, well, it's not easily convertible, it is a set of bytes. Really, raw data is a set of bytes, and you can easily use it as the message to sign. And in fact, in our encrypt and encrypt file and generate digital signature functionality, you can work not only with strings, but with any arbitrary Wolfram language expression or other object, which is pretty handy, because if you think of it, one can, if I want to tell everyone that this is the, for example, a piece of code, a program that I have written, and I want them to trust me and run it because I have written it, I can create a signature on the piece of code and, make people verify it. And so when they run it, they're gonna know that this has been created by me, and they trust me. It has not been created by some other person who claims to be me, and that the code was not modified, and this is the same code that I have sent to them, and so on. Because the examples on strings are pretty easy to make, but in fact, you can use basically any Wolfram language expression, and as well as an image. For example, in this part, we have taken an image of a little nice bird, and we have created a signature on this, and we have verified that in fact it is true. But if you use a different image of a bird, it becomes false. And if you modify the image, for example, I cannot tell that these two images are really different with my WRI. Maybe because I know they're different, I can say that, like, okay, yeah, this one is a little bit, the one on the right is a little bit more sharp. Because, I see here that we have been using sharpen to that. But, to someone, it looks pretty pretty equal. They look almost the same. But if you try to verify if it's actually the same picture that was signed by a person, it can give you false. And which is also a useful application because this deals with raw data and raw bytes, and the raw underlying data of this image has changed. And even if a human eye cannot detect it, the math and the multiplications on elliptic curves can. So it can save you by telling you this is in fact not the same thing. I guess for now, enough on signatures. We have a couple more examples. One of them is encrypting files, which is a very practical application. And two others are more about being able to study cryptography and teach cryptography. Yes, first we'll stop on a more practical application. Well, I guess I do not really have to explain the usefulness of being able to encrypt files, but if you want to keep your data or your results secret and not accessible to anyone, this is your way to go. For example, here I have a data set of the passengers of Titanic, which is basically a class of which person traveled, their age, their sex, and the fact if they have survived the crash or not. Now, this can be any other data we want to do. And so suppose we obtained some results, we did some survey, we did some calculations, we export this as a TSV because it's pretty handy for multi-column data. And this little piece of code uses two new things at the same time. So one is file encryption directly, and another thing is authentication dialog, which is going to prevent me from doing the same deliberate mistake as I did before of showing you the private key. This is not going to make me type password in the open, but it's going to make me type some password like this. Boom, like this. And now you're not able to see it, so you're not going to be able to decrypt my Titanic data set. And I saved it. But I also want to delete the original file. So now I only have this encrypted one. So nobody can access my research on passengers of Titanic. And next time I want to access it, I use again the authentication dialog, where I can type my password, which is not going to be saved anywhere, which is not going to appear on the screen. Because the other thing you can do here is you just go type password goes to the string that is your password. And I hope I remember my password well. No, I do not remember it anymore. Let's try again. Yes, now I do. So I have recreated the original file. And the next time I want to access my data, I do semantic import, which takes it from the raw TSV file and gives me back the same nice kind of data set as we have had before. and lets me work with it just as smooth as it has been before. But with the achievement of when I'm away, this data is not accessible by anyone else who doesn't know my password, because it has stored in the encrypted file, which is also nice if you're sharing a workstation with someone, for example. So I can talk about this for hours. I really like what we did, and the version 12 was launched, if I'm not mistaken, in the end of April. So it has been more than 6 months, and then we have also done new things. And there is still a lot to do and to go. So yes, I went through the practical applications of this. So we can go more to the theoretical ones. And we have these two last ones in the bottom here. One of them is showing the properties of digital signatures and showing us why, in fact, they are safe. So it always starts here with generating a new key pair, but in fact, you don't have to do it every time. You have to only generate it once and then export it, as we did in one of the previous examples. So any next time you want to use it, you just import it back and you use it. But because this is a theoretical exploration example, for the cleanliness of the experiment, we just generate a new key pair. And what we want to show here is that even if the messages are very, very similar to each other, like I showed before with Twitch method, Twitch test, and Twitch test with capital T, but here we are making it even more restrictive. We take in 1,000 of integers, which one integer is just different from another by just 1 bit. You know, they're very, very close. If you take the actual letters, they have more of a bit difference between each other, but this is just like row bits, and they're very close to each other. We can actually see that we get the sequential ones. And what we try to show here is that if we sign all of them, they are going to generate a completely different results. And we create a signature object. We get the two parts of R and S of the signature, as I've showed you before. And as we can see here, if you compare these plots, these are very scattered, these two plots in the bottom, compared to this. This shows us that digital signatures are, in fact, handling their job pretty well, telling us that different messages are not the same and that they create a completely different signatures. And one cannot just, you know, go and try to modify your message a little bit to be able to fraud, to be able to say, fraud your personality, or to be able to create a valid signature on a wrong message because they behave unpredictable. You see how scattered they are? They almost cover the whole field uniformly. So if this was actually uniform coverage, this would have been an ideal case, but because these things are limited by the fields they are defined on, you see it's not exactly uniform, but it's pretty close to. And what this shows is that, you know, if we would take one message and then we take a message that is just differs one bit, the values of R and S on elliptic curves are going to be completely different. They are probably going to be like almost every digit is going to be different. And the same holds for other digital signatures, like RSA ones that we are gonna launch soon. And the same also holds, for example, for the hash functions. And this kind of example shows that you can not only use the things for practical matters, but you can also do some more theoretical research on them. Because, for example, I was studying cryptography in the university, and findings like this here were a pretty big thing in our studies, because we had to prove the things are safe, we have to prove the things are random enough, we have to prove that in fact two similar messages generate completely different outputs, that two very similar keys generate scattered enough outputs. When you would do research and trying to invent, for example, new types of signatures, this is kind of the things that you have to look at. Or, for example, if I want to research another type of function, for example, an encryption method, and I generate this, and I see that, for example, the outputs are all gathered in one piece of this plane, or they are pretty close to each other, or they're not scattered enough, I can see that they are, in fact, not as good, and they are predictable. And that's what it has to be. It has to be unpredictable to be safe, to be unfraudable. And the last example that we can cover here is also about the more of mathematical exploration of the things. Because, as I said before, I really love cryptography for being a very mathematical, provable subject with very good practical applications. But this here is very mathematical. It is kind of similar to the previous one, though it works on hash functions. Hash function, its main goal is to, given some input, produce an output that is going to be irreversible, which says that when you have something that is produced by a hash function, you are unable to get back the original message that it was generated on. They are fast to generate, but they are impossible to revert. And one of the mathematical properties one has to look at for good hash functions is called the Avalanche Effect, which is a pretty good name if you think of it, because the avalanche starts from something small and it creates a disaster on its way and randomizes everything. So what a hash function does, well, we'll see now. Here we also create 10,000 random integers. And I don't think I'm going to run this example because I remember it has been a little bit slow because of the amount of things I was trying to hash at the same time. So we'll just scroll through this. So we have created 10,000 random integers. And what we're trying to do here, we're trying to create the pairs of inputs, which are going to be pretty similar to each other and are going to be differing only in 1 bit in the pair, for which we have written a little handy function that just flips a random bit in the input. And for example, this is the pair of integers that we have created here. That in integer form, you see they look pretty different, especially if you look on the last digits. They start differing somewhere after the 12th digit, I guess. But in fact, they only have 1 bit flipped. So we use thus 10,000 pairs, very similar to each other, as an input to a hash function. So having distance actually proves us that all these pairs only differ in 1 bit. You see that there are 10,000 pairs that differ in 1 bit. We create byte arrays for faster hashings, and we feed all of them to a hash function. For example, here we have chosen the Ketchuk 256, which is a new 12 hash function, but one can use any other hash function available in a language, or you can even write your own function that has properties and capabilities of the hash function and check it with this method. And so what Avalanche Effect has to do is to show us that even though our inputs only differ in 1 single bit out of all 256, the hash function is going to produce the result for these 2 very similar inputs that is going to be very, very different from each other. And to prove that, we use Hamming distance again to show us how many bits differ. That's what Hamming distance does. It says how many bits differ between 2 things. And we expected on the average that 2 results are going to be different in like half of the bits, which is 256 divided by 2, 128. And after we have here calculated all the distances between all the outputs, we see that in fact the mean is very close to 128, which is very good. Dun, 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 dun. And here is the nice plot that shows with all the output pairs, gives us a nice Gaussian that has its mean around 128. That of course there are inputs that differ in less bits, there are inputs that differ in more bits, but you see that there are none that differ in less than 100 bits, which is pretty good and pretty promising. And if someone is curious what you do when you study cryptography, you do a lot of this. I guess I'm finished with the examples, so I will be happy to receive feedback and what people think about this, about what things are going to be interesting to see in future versions. How can these examples be improved? Well, for example, this example of receiving encrypted messages can be improved by being able to receive encrypted files. For example, I don't know, if I'm a teacher and I want my students to submit me their researches, but without being able to look at each other's, I want them to send them to me encrypted, for example. And well, me and Konstantin here has been silently following us, promising to give you even more practical and interesting theoretical applications of the modern cryptography, maybe also historical cryptography. And thank you everyone for attention.